Hi there, Miss Barber here. This lesson is titled Hamilton Paths and Hamilton Circuits. Definitions. 1. A Hamilton path is a path that contains each vertex of a graph exactly once. 2. A Hamilton circuit is a path that begins and ends at the same vertex and passes through all other vertices of the graph exactly one time. Example, find a Hamilton path for each of the graphs provided. We consider figure A for a solution. For the graph of figure A, one possible Hamilton path will start at vertex A, go to B, then C, E, and D. We have hit each vertex once and only once. Let's consider, for the graph of figure B, one possible Hamilton path. I'll start at H. H to G to F to C to A, D, B, and E. In this path, we hit each vertex once and only once. Example, find a Hamilton circuit for the graph shown. Remember, a Hamilton circuit starts and ends at the same vertex. Solution, one possible Hamilton circuit. I'll start at A. My path will be A, C, E, G, H, F, D, B, back to A. We have tagged each vertex once and only once and ended up where we started. Take a few moments now for you to find your own Hamilton circuit. Example, find a Hamilton circuit for the shown graph. Our solution, there are many of them. One possible Hamilton circuit. I'll start at C. Travel to B, A, D, E, back to C. Before you continue, find another Hamilton circuit on your own. Example, determine a Hamilton circuit for the graph shown below. We have many options. One possible Hamilton circuit. I'll start at A. Travel from A to B to C to G to D to F, E, and back to A. Before you proceed, find another Hamilton circuit on your own. Definitions. 3. A complete graph is a graph that has an edge between each pair of its vertices. Provided for you are 3 different examples of complete graphs. Notice that for each of the graphs, there is an edge between each pair of its vertices. Example, consider the 2 graphs. Determine if they are complete and explain. We'll begin. The graph of figure A is not a complete graph. There is no edge connecting the vertices A and D, and no edge connecting the vertices B and E. The graph of figure B is a complete graph. Every pair of vertices is connected by an edge. How many Hamilton circuits? Any circuit that passes through the same vertices in the same order is considered the same. For example, consider the graph given with vertices A, B, C, and D and edges between all vertices. The path A, B, C, D, A and B, C, D, A, B and C, D, A, B, C and D, A, B, C, D. Each of the four paths above travels through A, B, C, and D in a clockwise direction. They are considered the same Hamilton path. Example, list all the Hamilton circuits for this given graph. For a solution, to avoid duplication when forming Hamilton circuits, we'll begin at A. Then we'll have one beginning at A, 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 and A. And then we'll all end at A as well. That is, each one starting at A will end at A. And now we're going to form permutations of the remaining three vertices. We'll start with B, C, and D. Then we'll have B, D, and C. We'll have C, B, and D. And then we'll switch the B and D, so we'll have C, D, and B. Our next permutation of the inside three vertices will be D, B, and C, and we'll switch B and C to have D, C, and B. And each of these 6 different Hamilton circuits can be written in 4 different ways. Those 4 different ways represent the same circuit. Definition. The number of unique Hamilton circuits in a complete graph with n vertices is n minus 1 factorial, where n minus 1 factorial is defined as n minus 1 times n minus 2 times n minus 3 all the way to 3 times 2 times 1. Example, how many unique Hamilton circuits does a complete graph with the following number of vertices have? Part A, 5. That means n equals 5, and the number of unique Hamilton circuits is computed as n minus 1 factorial. So that'll be 5 minus 1 factorial, which is 4 factorial, and you can compute 4 factorial in your calculator. You'll get 24. Part B, how about 9 vertices? That means n equals 9, and the number of unique Hamilton circuits is n minus 1 factorial, so we need to compute 9 minus 1 factorial, which is 8 factorial. You can use your calculator to do the 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or the factorial feature. Either way, the result is 40,320. More definitions. Definition 5. A complete graph whose edges have numbers attached to them is called a weighted graph. The numbers shown along the edges of a weighted graph are called the weights of the edges. The graph below is a model for one-way airfares for cities A, B, C, D. Use the weighted graph to find the cost of the trip for a Hamilton circuit A to B to D to C to A. Let's begin. Our first leg of the trip is A to B, and that's a $210 flight. The next leg is B to D, and that's a $375 flight. The flight from D to C is $575, and the flight from C to A, that's back to our starting point, is $125. The total cost of the trip is the sum of the 4 air fares. That's $210 plus $375 plus $575 plus $125. The total is $1,285. The traveling salesperson problem. The traveling salesperson problem is the problem of finding a Hamilton circuit in a complete weighted graph for which the sum of the weights of the edges is a minimum. Such a Hamilton circuit is called the optimal Hamilton circuit or the optimal solution. One method for finding an optimal Hamilton circuit is called the brute force method. The brute force method of solving the traveling salesman problems. To determine the optimal solution, 1. Represent the problem with a complete weighted graph. 2. List all possible Hamilton circuits for this graph. 3. Determine the cost or distance associated with each of these Hamilton circuits. And 4. The Hamilton circuit with the lowest cost or shortest distance is the optimal solution. Example: find a minimum Hamilton circuit for the complete weighted graph shown by the brute force method. Our solution: we need to list all the Hamilton circuits first. Since there are 4 vertices, A, B, C, and D, there are 4 minus 1 factorial, which is 3 factorial, or 6 possible circuits. The table provided gives us 3 of the circuits completed. We'll do a few by ourselves. The first circuit I'd like for us to consider is A, B, C, D back to A. The table gives A, B, D, C, A. Now we'll do A, C, B, D, A. And we'll also do A, C, D, B, A. The table gives the values for A, D, B, C, A and A, D, C, B, A. Now let's write the weights of each leg. From A to B, it's 4. From B to C, we've got 6. From C to D, the weight is 3. And finally, the last leg, that would be D to A, that's 10. The total is 23. Let's do this for A, C, B, D, A as well. So from A to C, that length is 2. From C to B, that weight is 6. From B to D, that weight is 7. And D back to A, that weight is 10. And the sum is 25. Now, pause the video and you compute each of the legs for A, C, D, B, A and the total. After you do that, resume the video and we'll compare answers. By looking at this completed table, we see that the minimum amount for this graph is 16. And notice that there are 2 different paths or circuits that you can use to get the minimum amount. Nearest neighbor method. Notice the word approximate. To approximate an optimal solution using the nearest neighbor method, first, represent the problem with a complete weighted graph. Next, identify the starting vertex. 3. Of all the edges attached to the starting vertex, choose the edge that has the smallest weight. This edge is generally either the shortest distance or the lowest cost. Travel along this edge to the second vertex. 4. At the second vertex, choose the edge that has the smallest weight that does not lead to a vertex that's already visited. Travel along this edge to the third vertex. Step 5. Continue this process each time moving along the edge with the smallest weight until all vertices are visited. Then finally, step 6. Travel back to the original vertex. Example, an appliance repairman must repair 4 appliances at the locations shown in the graph below. The estimated travel time in minutes is shown between the 4 locations. The repairman wants to visit the 4 locations in an order that takes the least amount of time. Use the nearest neighbor algorithm to find an approximate solution to this problem. We need to choose a starting vertex, so I'll choose A. Next, choose edge with the smallest weight. That's either AB or AE. Let's choose AE. The value is 8. At E, choose the edge that has the smallest weight. EC is 4. Next, choose CB at 3. Continue moving along the edge with the smallest weight. Our circuit is A, E, C, B, D, A, and the weight is 8 plus 4 plus 3 plus 9 plus 13. The result is 37. We computed the weight of the circuit starting at vertex A as 37. We need the respective weights of the circuit starting at B, C, D, and E to determine the optimal/minimum travel time. The table has solutions for circuits starting at C and E. We need to compute total weight starting at vertices B and D. Let's start with B. B to C is least with 3. C to E is least with 4. E to D is the smallest with a weight of 6. A is our only option from D, and that weight is 13. A back to our starting vertex B is 8. The total of 3 plus 4 plus 6 plus 13 plus 8 is 34. Now, pause the video as you use the traveling salesperson algorithm to find a circuit with a starting vertex at D. When you finish, resume the video. My path with D was D, E, C, B, A, D. The sum is 34. Did our values match? We see that paths B, C, E, D, A, B and D, E, C, B, A, D both have the optimum or least travel time of 34 minutes.